Hello friends, in this video we are going to derive an equation related with momentum integral equation. It is given by von Karman, hence it is von Karman momentum integral equation. So let's start with the video. Let's start with basic concept related with boundary layer. If flow velocity is capital U as shown in figure, this U, and if a plate is surrounded by flow, then in that case the boundary layer is formed surrounding to the plate. So this is boundary layer. Thickness of boundary layer goes on increasing with respect to x distance, this distance x, starting from this axis system, this is x and this is y. So it is clear that some mass outside the boundary layer is entering into the boundary layer region. Hence, this is the reason for increase in the thickness. But correspondingly, there are various changes related with thickness as well as momentum. So, we will see a derivation regarding them. So, this concept was first given by this scientist von Karman. Hence, we will call this derivation as von Karman momentum integral equation. This equation is also useful to calculate a drag force on flat plate. So this is the derivation for calculation of drag force. We all know that drag force is nothing but the force which is resisting the motion, which is acting as a shear stress or shear force and acting on the surface. So for 3-dimension imagination, I can say that if this is the width of a plate, say B, then in that case that drag force acts along the surface, this dx and b. I have considered a strip A, B, C, D. After magnification it will look something like this, A, B, C, D, this portion. So it is clear that at point A, whatever is the depth that is increased at point B by this much amount as shown in figure. So correspondingly we will find the derivation for the changes. Let's start with the actual derivation. I can say according to Newton's law of viscosity, shear stress tau is equal to mu du upon dy. This du upon dy is called as velocity gradient or rate of shear strain. In our case we will call it as tau nod. So this is nothing but the shear stress acting on plate. Shear force can be calculated on this plate. The stresses are acting along the surfaces like this as arrow shown in figure. So shear force is nothing but the shear stress tau nod into area under consideration. Here area is this dx into this width b. So it will be dx into b. As we all know, a rate of change of momentum is nothing but the force. So first we will calculate force and we will equate it to the rate of change of momentum which is occurring on the plate. So first of all, to calculate momentum we had to find mass transfer rate. So mass transfer rate through portion AD. Say for example, I am showing some mass as m or m1. So this mass m1 is entering through section AD. So this mass transfer rate m1 can be calculated as integral 0 to del rho into V into area of strip. Hence 0 to del rho into, here velocity entering in section AD is u, so u, rho into u into width is b, and height, any height, is dy. dy is the depth at which small u velocity is being calculated, so it is dy. Similarly, mass transfer rate through, this was the portion A, B, C and D. So mass transfer rate, this was m1 through BC, means this, highlighting the mass transfer rate, I will call it as m2. So m2 is equal to m1 plus rate of change of mass transfer, that is delta by delta x mass through AD dx. So I can write in the equation form as integral 0 to del rho u b dy plus delta by delta x, I will write it in square bracket, again integral 0 to del rho u b dy outside the square bracket dx. So by continuity equation, for incompressible flow, I can say mass entering DC, this is the curved portion DC, and mass entering through DC is this one. Okay, so this mass which has been entered can be calculated as difference between masses, that is m2 minus m1. So m2 minus m1, we all know that in m2 this part m1 plus this much addition is been added. So obviously m2 minus m1 will be this term. So it is delta by delta x integral from 0 to del rho u b dy outside the square bracket dx. If we have calculated mass entering, then in that case next step is to calculate momentum flux. So momentum flux entering through AD is 0 to del, momentum is mass into velocity, so rho u b dy, this is mass into velocity at AD, velocity is u, so into small u, so it becomes 0 to del rho u square b dy. Momentum flux leaving through BC, I have to draw a diagram. This is A, this is B, this is C, this is D. So through BC is nothing but the 0 to del rho u square b dy. This was rho u square b dy, integral of 0 to del, plus rate of change of same, that is 0 to del rho u square b dy into dx. So we can have equation as same, in the same manner, momentum flux entering through DC part, that is this one. This one is nothing but the difference between this second term minus first time. So that is equal to this square bracketed term, this one. So that is equal to dabba by dabba x integral 0 to del rho u square b dy. Same is the process for mass transfer rate, this one. But it is actually entering fluid is with velocity capital U. So I can write it as dabba by dabba x 0 to del rho u b dy bracket complete into dx into capital U, where u is nothing but the free stream velocity. Momentum flux entering through DC. Through DC, the velocity entering is at capital U, so it can be written as dabba by dabba x of 0 to del rho u b dy dx into this capital U. So rate of change of momentum of control volume is momentum flux through BC, this what, minus momentum flux through AD, that is this one, minus momentum flux through DC. So we have derived all the three things, just doing the calculations as per formula. That is, initially momentum through BC is integral of 0 to del rho u square b dy plus dabba by dabba x integral 0 to del rho u square b dy dx. This is the first term, minus second term is 0 to del rho u square b dy minus dabba of dabba x 0 to d rho u capital U b dy outside the bracket dx. This is the second term. This is the third term. This was the first term. So 1 minus 2 minus 3, totally it will become dabba by dabba x of rho b is constant integral 0 to del in bracket this u square minus this u into capital U. See, these two terms are already get cancelled. So whatever is the difference is this minus this into dy completion of square bracket times dx. This term rho b is being a constant. I can take it outside the differentiation as rho b into dabba and dabba x of integral 0 to del u square minus u into capital U into dy into dx. This is the rate of change of momentum, equating it with this shear force equating with shear force we have tau naught dx into b is equal to rho b dabba and dabba x integral 0 to del u square minus u into capital U dy to dx. This is negative side, so that can be equal to dabba by dabba x integral 0 to del u minus u square. I am considering this negative sign by changing the two terms, that is this one and this one. So tau naught into b is equal to rho of dabba by dabba x of integral 0 to del small u into capital U minus u square dy to dx. I know that there are some equations in which small u upon capital U value is being considered, and that equations are nothing but the related with thicknesses, that is momentum thickness and etc. So I will try to convert this equation in their form. So I can change the format of this equation by introducing new terms in the equation as rho into capital U square. I am multiplying capital U square to a whole equation. It means that I have to divide all these things to the shown part, this part. So it becomes dabba by dabba x integral 0 to del. This will become small u upon capital U minus small u square upon capital U square dy into dx. I can take small u upon capital U as common, so we can have rho u square dabba by dabba x in square bracket 0 to del small u upon capital U as common 1 minus small u upon capital U dy into dx. This term, this highlighted term, is nothing but the momentum thickness theta. This is the formula for momentum thickness. Momentum thickness is that thickness which, when displaced by a plate, compensates the changes in the momentum. So we will have tau naught as rho into u square into dabba by dabba x of theta. So I can say that tau naught upon rho u square is equal to dabba theta upon dabba x. So this equation is von Karman momentum integral equation. Its application is, first, to calculate drag force, as drag force is equal to 0 to length d into fd, that is 0 to length L, tau naught into b into dx. So to calculate tau naught, we will require that equation. So this equation is very important. We should know this for solving the problems in further region. I can say tau naught is equal to rho u square dabba theta upon dabba x. That's all. Thank you.